Hi, so this talk is about indistinguishability obfuscation, range avoidance, and bounded arithmetic. I'm Rahul, and this is joint work with Jiatu and Ryan Williams. So in this talk, I'm going to tell you about how this cryptographic object called obfuscation lets you answer two related questions in the areas of de-randomization and in logic. The structure of this talk is going to look like, first we're going to explain what exactly this question is. You don't need to know any background about de-randomization or logic or obfuscation for this talk. I'm going to tell you what this problem circuit range avoidance is. Then we're going to move on into logic, explain what this question is. Then I'll tell you a little bit about our results and the background you need on obfuscation. And finally, I'll say a little bit about how this result is proved. Okay, great. So what is this problem, circuit range avoidance, and what is the main open question here? So circuit range avoidance is a problem that was first defined by Kleinberg, Korten, and Milchopolsky in 1921, and they were in particular interested in total function problems in the polynomial hierarchy. The problem itself is very nice. It takes as input as some circuit C that maps n bits to m bits, and the important part is the codomain of the circuit is larger than the domain. In particular here, m is greater than n. I like to consider the case where, like, let's say m is equal to n squared or something like that. And your goal is to output some string y that is not in the range of C. And just to be clear, this is a total function problem because there always exists such a string. In fact, there are many such strings in the setting, say, where m is equal to n squared, all but an exponentially small fraction of strings are going to be outside the range of the circuit C. Okay, so just to give you an example, a very simple example, in the case that the circuit being fed as input is, say, a squaring circuit, which takes as input a string x and then squares its input, then you'd want to output some string y that is not a square number. This is just a simple example of the avoid task for some specific circuit. Okay, so what do we know about the complexity of avoid? In particular, what upper bounds do we know on the problem? So there's a very simple upper bound that shows that there's a randomized algorithm for the problem. In particular, if you just output a uniformly random string in the codomain, then this is going to work, except with probability 2 to the n minus m, which if m is larger than m is at most 1/2, and if m is equal to n squared, this is exponentially small. So there's a very simple randomized algorithm. In fact, it doesn't even really have to look at the circuit at all, besides knowing what the number of outputs bits are. And so this shows that avoid is in FBPP, where F here stands for like the function version of BPP. I mean, some people define FBPP differently, but for this talk, this was what that means. And if one had an MP oracle, you could even improve this upper bound to have to be a zero-error randomized algorithm by just, you pick a random string and then you use the NP oracle to check it's not in the range. And in fact, you can actually de-randomize this under some plausible de-randomization assumption. Kind of the interesting question for this talk is going to be, can you de-randomize this algorithm? In particular, is there a deterministic algorithm for range avoidance? And what makes this question particularly interesting is it's not really clear what the answer should be. In fact, Ren Wang and Santhanam remark in one of their papers, is unknown whether avoid in FNP, avoid in FP, or the negations are applied by any plausible assumptions. As far as we know, we do not even have a good idea of what the ground truth should be. So kind of one of the main contributions of this work is to use the idea of obfuscation to actually point to what we think the ground truth should be. So even though previously we didn't have a good idea of whether deterministic algorithms for range avoidance should exist or not, we did know that deterministic algorithms for range avoidance had pretty significant consequences in both combinatorics and complexity theory. Particularly, they would imply breakthrough so-called explicit constructions. In particular, a sequence of works note that it would imply, for example, explicit hard truth tables with exponential circuit complexity, rigid matrices, strongly explicit Ramsey graphs, strongly explicit two-source extractors with optimal parameters, And for this talk, it's not so important what exactly these objects are. These are just kind of long-standing open questions in combinatorics to construct explicit examples of these objects. One thing that I want to emphasize is explicit constructions of these objects are things that we believe should exist. So this doesn't exactly say that there shouldn't be a deterministic algorithm for range avoidance. It just says if one exists, then it would have some pretty dramatic consequences we believe, but we just don't know how to prove yet. So it doesn't say that there should be a deterministic algorithm for avoid or not. It just says if there is one, it's going to be hard to show it unconditionally. Okay, so far I've told you a little bit about this first question. Hopefully it's clear. Is there a deterministic algorithm for circuit range avoidance? Next, I'm going to talk about logic, and in particular this area called bounded arithmetic, and explain this question. Okay, so bounded arithmetic is an area of logic which tries to understand the length of proofs in fragments of piano arithmetic. So basically what it does is it says, if I give you these axioms for some list of axioms, what's the length of the shortest proof for various statements? So one of the central objects in bounded arithmetic is called PV1. In some sense, it corresponds to polynomial time reasoning. It was created by Steve Cook, so it's often called Cook's theory. And so I'm not going to say too much about what PV1 is and what the axioms it has are, but I wanted to just give you some very brief flavor of what PV1 is. On the one hand, it's relatively weak in that it can't, for example, prove that any one-way permutation is surjective. And if you look at some of the candidate one-way permutations, these are often things that kind of are very easy to see are surjective, but somehow it's hard to prove using PV1. So that gives you some indication that maybe this proof system is relatively weak. On the other hand, PV1 proves some fairly deep statements. So for example, Jan Peek showed in 2015 that you could actually prove the PCP theorem using PV1. So in some sense it can be weak, in some sense it can be strong. Somehow this is corresponding to it being polynomial time reasoning. Okay, so one important question about PV1 that was kind of first studied by Krychek in 2001 and kind of inspired him to come up with this notion of proof complexity generators, if you're familiar with that, is does PV1 prove the dual weak pigeonhole principle, whatever that is? So what is the dual weak pigeonhole principle? The dual weak pigeonhole principle is a very simple statement. It says that if there are n pigeons and 2 n holes, then there must be an empty hole. So this is like a dual version of the pigeonhole principle, because instead of arguing about a hole with 2 pigeons in it, you're arguing about an empty hole, and it's weak because there's this n versus 2n. There's like a constant factor difference there. And so one particular consequence of the dual weak pigeonhole principle is that you can use it to prove Shannon's counting argument, that there is a Boolean function that requires circuits of size 2 to the n over n. And this is part of the reason why showing that the dual weak pigeonhole principle cannot be proved using efficient reasoning is interesting, because it's kind of a baby step to understanding whether or not efficient reasoning can prove circuit lower bounds. And so that's kind of the motivation for this question. Okay, so now hopefully I've told you, explained what these two questions are and kind of why they're interesting. Next, I want to say a little bit about our results. To do this, I'm going to have to mention some stuff about obfuscation. I'll just say it very informally, and then after I state the results, we'll actually define what the notions of obfuscation that we need are. Okay. So what are the main results that we prove? So our main theorems are as follows. Assuming the existence of some notion of obfuscation that I'm going to tell you about in the next 2 slides, and that NP is not in co-AM infinitely often. So co-AM stands for co-Arthur Merlin, which is basically the probabilistic version of co-NP. So if you believe in de-randomization, then this should be NP not in co-NP infinitely often. There is in fact no efficient deterministic algorithm for void, and also PV1 cannot prove the dual weak pigeonhole principle. So under these two assumptions, this one is very standard complexity theoretic assumption. As we'll see later, this has become a standard cryptographic assumption, or at least a widely believed cryptographic assumption. You can actually show that the answer to the two questions on that outline slide is actually both no. PB1 cannot prove the Dewey pigeonhole principle, and there's no efficient deterministic algorithm. Okay, so next we're going to take a brief interlude to talk about obfuscation and define exactly what sub-exponentially secure I/O means. Okay, so what is cryptographic obfuscation? So this is kind of a line of work that was initiated by this landmark paper of Barak et al. In 2001. And so the idea of obfuscation is that you're handed some circuit C, and you want to hand back an obfuscated version of C, some sort of scrambled version of the original circuit that still computes the same function, but is kind of obfuscated in the sense that like all you can do with this circuit is run it. It doesn't reveal anything else except the function values of the circuit. And the way that that's formalized is some version of this, somehow that like anything you can compute given the obfuscation, you can also compute given black box access to the function computed by C. And I'm being a bit informal here because it turns out that this ideal version that you would want actually doesn't exist. So this paper by Barak et al. Actually shows that this construction of obfuscation, or this notion of obfuscation, is actually unachievable. So in the same paper, they propose a weaker notion of obfuscation called Indistinguishability Obfuscation, and which is as follows. So a randomized algorithm, I/O stands for Indistinguishability Obfuscation, it'll take as input 1 to the lambda. This is some sort of security parameter thing. Don't worry about that for now. It'll also take as input some circuit C, and it'll have the following two properties. So if I/O is this will be an indistinguishably obfuscator if it has perfect functionality and sub-exponential security. I'll tell you what that means next. So perfect functionality means that for all circuit C, I/O of C will output some circuit that computes the same function as C. And it'll be important later for our results that this is like really perfect. It's like every single time, not just with high probability, I/O of C will output a circuit computing the same function. The other property is the notion of security is that for any two circuits of roughly the same size that compute the same function, no adversary can tell between the I/O of C and the I/O of C prime. So if you have two circuits that compute the same function, their obfuscations are going to be basically indistinguishable up to some very small probability. And so it might not be clear a priori why this security guarantee is all that strong in this, because like you're only saying that if you have two circuits that compute the same function, you can't tell. It's not clear how you do things interesting things with this, but don't worry about that so much for now. And the last thing I want to say about indistinguishability obfuscation is that there's a recent really breakthrough work by Jiatu and Sahai that showed that actually sub-exponentially secure indistinguishability obfuscation exists under well-founded assumptions. So this has now become kind of a widely believed assumption in cryptography. And so now just to recap our results, we show that assuming sub-exponentially secure in particular is assuming the I/O that Jiatu and Sahai show exists under these well-founded assumptions, and basically NP not equal to co-NP, you get the two consequences about avoid and about PB1. So in the remainder of the talk, I just want to give you some of the ideas involved in proving this first result, that there is no efficient deterministic algorithm for avoid. The second result will build on the first thing, but will involve some more details that I won't have time to get into in this talk. Okay, so now my goal is to explain at least some of the intuition behind this first result. Why does NP not and co-AM and sub-exponentially secure I/O imply that there's no efficient deterministic algorithm for avoiding? So here is an idea, or at least an intuition. Suppose you handed me a deterministic algorithm for a void. My goal is to get a contradiction. I want to get a proof by contradiction that this thing can't exist. So I say, you hand me it, and I want to prove that something strange happens. So what might be the something strange that happens? And in particular, I want this something strange to happen for a deterministic algorithm, because we already know that a randomized algorithm exists. So one thing that's somewhat strange that you can do if you had a deterministic algorithm for a void is that for any circuit C, you can prove that some string y is not in the range of C. How do you do that? You just run the avoid algorithm on C, and this, in some loose sense, will constitute a proof that y is not in the range of C. Because if this avoid algorithm is correct, then it has to output some y that's not in the range of C. And it's important here that this is a deterministic algorithm. If it's a randomized algorithm, well, it could fail, so then you don't know for sure that y is not going to be in the range of C. But if this is a deterministic algorithm, for any circuit, you can always prove that there's some string that's not in the range of the circuit. And a priori, this maybe doesn't seem like something you should be able to do. I mean, if I hand you an arbitrary circuit C, why should you be able to get a short proof that something's not in the range of the circuit? A priori, it seems like you would have to evaluate that circuit on all points in order to show that something's not in the range of the circuit. So this question of whether short proofs exists, kind of ties back into this NP versus co-NP assumption, because NP versus co-NP is really about does checking whether a circuit is unsatisfiable have short proofs or not. So it's a kind of a complexity theoretic formalization of when things have short proofs or not. So that kind of motivates this NP versus co-NP assumption. Okay. In particular, the proof of that avoid theorem is going to look like this. It'll say, if we have sub-exponentially secure I/O, and if you have a deterministic algorithm for void, then that will imply that NP is equal to co-NP. And actually, I'll show you what the reduction is. In particular, specifically, we'll show that there is a non-deterministic polynomial time algorithm that will check if a formula is unsatisfiable. And we'll show that NP is equal to co-NP. So what does that algorithm look like? So the algorithm, I called it reduction here, will work as follows. It will be given some formula phi on n inputs, and it will say it's unsatisfiable if and only if there exists some y and exists some r such that the following holds. Such that, and I'm going to unpack this, when you run the deterministic algorithm for void, which I've abused notation and just written it as a void, which also stands for the problem, but for the sake of simplicity, it also stands for the algorithm. When you run a void, on the obfuscation, again, I've done the same thing where I've written I/O for the algorithm, of some circuit C that's built from phi and y. Don't worry about this for now. It's some circuit C that you can build efficiently from phi and y. When you run the obfuscation algorithm on C, on this circuit C, with randomness r, and you feed that to the void algorithm, you get back y. And I want to stress, hopefully it's clear that this is like a non-deterministic polynomial time algorithm, because it makes some guesses, it guesses y and r, and then it checks this condition, and this condition is polytime checkable, because the I/O is polytime, avoid is polytime, C, as you'll see later, can be built efficiently. So again, you guess y and r, and you see if when you run avoid on the obfuscation of some circuit, you get back y. So what exactly is this circuit? Oh, also you'll have to set the security parameter or something, but let's not worry about that for now. So what is this circuit? The circuit will look like as follows. It's going to output 0 on input x if the formula is not satisfied at x, and it's going to output y if phi is satisfied at x. And if you're familiar with witness encryption, this kind of corresponds to witness encryption when you plug it into I/O. Don't worry about that if you are not familiar with that. And so 2 points about this circuit. it maps n bits to n squared bits, basically by construction, so it's a valid input to avoid, and also its range is actually really small. There's actually only two things in its range, all zeros and y. Okay. Now I want to tell you, I've told you the algorithm. There are kind of two steps next to show that this indeed is a sound algorithm and a complete algorithm. So the first thing I want to tell you about is soundness, which basically says if the reduction says unsatisfiable, then phi is indeed unsatisfiable. And just as a reminder, I've put like the reduction up here in the top right corner. So the way you argue soundness is as follows. You say, well, if the reduction says phi is unsatisfiable, then basically by construction of the reduction, that means that there's some r and there's some y, such that this condition holds. Then, by avoid correctness, you know that y is not in the range of this circuit, because you assumed this is a good algorithm for avoid, and that's what avoid does. Then, by the perfect functionality of I/O, you know that the circuit output by I/O is computing the same function as the circuit it was given as input. So you know now y is not in the range of C phi y. And basically by the definition of C phi y, you'll now get that phi is unsatisfiable, because y will be in the range of the circuit if phi is ever satisfied. So this is how you argue for soundness. Essentially amounts to like going through the construction and just plugging things in. Okay, so the harder direction is completeness, which is where you want to show that if phi is unsatisfiable, then the reduction indeed says unsatisfiable. So I'll go through this a little quickly, but hopefully it'll give you the main idea of how this is done. Again, as a reminder, I'll put the reduction in the top right corner. So you say, okay, let phi be some arbitrary unsatisfiable formula. My goal is to say that the reduction must say unsat. In particular, I need to show that there exists a y and an r such that this condition holds. So what I'm going to do is I'm going to say, okay, let me just look at the distribution of this guy when I plug in y equal to 1 to the all 1 string and a uniformly random r. This is just going to be some distribution on strings, and by the correctness of the avoid algorithm, this is going to be, in particular, output strings of length n squared. And because it's outputting strings of length n squared, I know that there must be at least one string that is output with probability at least 2 to the minus n squared. So that's what this says. There's some y star such that when you run avoid on this circuit, it'll output y star with probability at least 2 to the minus n squared. This is just by some averaging argument. Now, the crucial thing to note is that since phi is unsatisfiable, C phi of the all 1 string and C phi of y star compute the same function. They always output all zeros. Because remember, C phi y will output 0 if phi is not satisfied at x, and output y if it is satisfied at x. So if you have some unsatisfiable formula, these two things are both going to compute the same function. And then you can use I/O security to say, well, the probability that avoid, when run on I/O of C phi y star, outputs y star, needs to be the probability that it outputted y star when you plugged in the all 1 string, which we already said happened with probability at least 2 to the minus n squared. You get some small loss from I/O security, but you can set the security parameter large enough, and this implies that there indeed exists an R such that avoid of I/O C phi y star equals y star. And so then by the definition of reduction, means you output unsat. Okay, so hopefully that gives you some of the ideas behind the theorems. If you have any questions, feel free to email me or Ryan or Jiatu. I'll be happy to answer them, and I hope you enjoyed the talk.